A research agent that cannot be evaluated cannot be trusted. Evaluation is not a check you run after a system is built. It is the foundation every comparison, every claim of improvement, and eventually every automated search rests on. This video builds the evaluation harness, the reusable module that scores a candidate against ground truth. This assumes you're comfortable directing an agent to write code and reading the diff it produces. Here is the ground we cover: the harness and its three splits, why the score must be automatic, the data flow that keeps it honest, and the leakage that corrupts it. Scoring, error, parsimony, and their sum. Evaluation hacking, oracles and judges, and the harness as a contract. Start with the definition. An evaluation harness is two things: a dataset and a scoring function that takes a candidate artifact and returns a number. The dataset is split three ways before any modeling begins: a training split, on which the agent may fit parameters; a validation split, against which candidates are scored and selected over and over across a search; and a held-out test split, reserved for a single audit at the very end. Three roles, and they must stay distinct. Training fits, validation selects, and later becomes the fitness signal a search queries. The final test supports the one generalization claim you make at the end. Why must the score be automatic, computed without a human in the loop? 3 reasons. Speed. An automated harness scores hundreds of candidates in the time a human scores one. Consistency. Automated scores are repeatable under controlled conditions, fixed data, seed, and environment where human judgments drift. And composability. A number can be compared, optimized, and used directly as a fitness signal. An evaluation that needs a human cannot drive an automated search. And what makes a score good? 4 marks. It is faithful. High scores mean genuinely good artifacts, not ones that exploit a loophole. Discriminating. It separates candidates of different quality. Leakage resistant. It cannot be improved by peeking at held-out data. And stable. Small changes in the artifact produce small changes in the score. Here is the sanctioned flow and the one forbidden path. The dataset is split first, before you look, into train, validation, and a sealed test. Train reaches the agent, which builds a candidate. The candidate is scored on the validation split, and that score is queried many times as the search runs. The winner, and only the winner, is read against the sealed test, exactly once. That test split is inviolable. It must not fit a parameter, tune a setting, or choose among candidates. The moment any information about it touches the artifact, the test score is optimistic and the generalization claim is compromised. Leakage is any arrow from the held-out data back to how a candidate is built or selected. Every mistake we are about to see is a disguised version of this one forbidden arrow. Leakage is the unintended exposure of held-out data to the artifact while it is being built. It inflates the score, making a weak artifact look strong. It takes several forms, in increasing subtlety. 1. Scoring on training data. The function returns error on the data the model was fit on. An overfit artifact memorizes it and posts a near-perfect score. 2. Constructing a feature from the whole dataset. Compute a normalization mean over everything before splitting, and information from the held-out rows has already bled into training. 3. Adaptive resplitting. Try many splits. Keep the one that scores your candidate best. The split is no longer independent of the artifact, and a form unique to agents that use tools. An agent that can search the web or run code may, at evaluation time, retrieve the benchmark's own answer key, collapsing solve the task into solve the evaluation. A fair harness for such an agent must sandbox its tools and scrub its environment, not merely partition the data. The defense is structural. Separate the split from the fit from the score. Split the data once up front with a fixed seed. Pull out the validation rows. Then build a scoring function that closes over those rows and hand back only the function. The caller receives a score, not the data. The validation rows are sealed inside the closure. But be honest about what this is. It is a reminder, not a wall. A Python closure can be inspected, and, more to the point, querying the same validation split thousands of times adaptively overfits it even when no raw row is ever exposed. So the held-out final test lives behind a separate one-shot report the search simply cannot call. Now the score itself, The most natural score for a model discovery task is predictive error. How well does the discovered model predict targets it was not fit on? The workhorse is mean squared error. For each point in the validation split, take the model's prediction, subtract the true value, square the difference, and average over all the points. Squaring does two things. It makes every term positive, and it penalizes large errors quadratically, so one big miss hurts far more than several small ones. It is also smooth, which makes it friendly to gradient-based methods. And the convention fixed for the rest of this video sequence. Lower is better. On a leaderboard of mean squared error, the smaller number wins. But error alone is not enough. A model that fits the data perfectly by memorizing it is not a discovery. Parsimony is the preference for simpler models among those of comparable accuracy. We measure it by complexity, the number of nodes in the expression tree, counting every operator, every variable, and every constant as one node. Take two expressions, x squared, and x squared plus a billionth times x to the seventh. On clean data, they may reach almost the same error, but x squared has 3 nodes, the variable, the exponent, and the power. The second has 9. Parsimony picks the smaller tree. A simpler model is easier to interpret, more likely to generalize, and less likely to be an accidental fit to noise. To select on both at once, combine them into a single number. The composite score is the error plus a parsimony weight, lambda, times the complexity. Lower is better, so a candidate is rewarded for low error and punished for extra nodes. That weight, lambda, is the whole trade-off in one knob. Too small, and the optimizer ignores complexity and chases accuracy into overfitting. Too large, and it ignores accuracy and returns something trivially simple. Its right value depends on the scale of the error and the expected complexity of the answer, so it is a deliberate design choice. And crucially, everyone comparing on the same leaderboard must use the same lambda, or the entries are not comparable at all. Now the deepest problem. Point an optimizer at a score, and it will optimize the score, not the goal. This is Goodhart's law. Any metric that becomes a target ceases to be a good metric. The stronger and more persistent the optimizer, the more aggressively it finds and exploits every gap between the score and genuine quality. Design a harness you would trust an adversary to attack, not one that merely looks good on the first round of honest candidates. The attack surfaces are concrete. Capacity hidden in a fitted constant, sine of c times x has only a few nodes, but by tuning that one constant it can fit arbitrarily many wiggles, so node count calls it simpler than it is. A high-degree polynomial that drives error to near zero on any finite dataset. Memorizing the data as a piecewise function. And Goodhart has a slower, temporal form. A benchmark that cleanly separates strong from weak today can saturate as capability rises, its scores bunching at the ceiling until the metric no longer discriminates. The response: grade the outcome rather than a fixed path, and when a benchmark saturates, graduate it, retire it to a regression check, and author harder problems. Not every output can be scored by a formula. How a harness computes its score varies along a spectrum of evaluability set by the task itself. At the verifiable end, an oracle settles quality automatically and cheaply, the mean squared error of a fitted model, whether a program passes its tests, the density of a sphere packing. A check the artifact either passes or does not, hard to argue with. This is the regime an automated search reaches furthest in, because a clean oracle is exactly what a tireless optimizer needs. At the judgment end, no formula exists. When the artifact is a proof sketch, a literature summary, or a piece of prose, a capable model must act as the evaluator, scoring the candidate against a rubric. It is the same harness contract, with the scoring function realized by a model call instead of a metric. Automatic, in that no human is in the loop without being objective. 2 cautions. Verifiability is a property of the problem, not a preference. Though the boundary moves, a proof becomes verifiable the moment it is formalized in a proof checker. And a judge is itself a target, so an optimizer will exploit a weak judge as readily as a weak metric. That is why the verifiable end, where it exists, stays the gold standard. One last property ties it together. The harness is a contract, a stable interface, a score function that returns a single number, lower is better, and a report function that returns the breakdown, the error, the complexity, and the composite score. A harness with this interface can be dropped into any stage of the work, unchanged. That stability is the point. The same reusable validation harness, unchanged, becomes the fitness function a later search calls thousands of times. The final test is deliberately not part of that interface. It is a separate one-shot audit, wired into nothing. This is one instance of a broader practice. The field compares agents on shared capability benchmarks, SWE Bench for real software issues, Web Arena for the web, Gaia for general assistance, OS World for computer use, each a named public harness with its own contract. A sealed test, a stable interface, a leakage-resistant score. The discipline is the same at any scale. Here is the evaluation harness on one card. The split, train fits, validation selects, a sealed test audits once. The score, error plus a parsimony weight times complexity, lower is better. The defense, leakage is any error from the held-out data, and Goodhart says a metric under pressure bends. The judge, an oracle where a formula exists, a model against a rubric where none does. The contract, a stable interface, reused unchanged. And the key idea to carry away. A reusable validation harness becomes fitness. A final test harness remains an audit. Build them cleanly, because everything you measure, and eventually everything a search optimizes, rests on the honesty of the score.